All right, awesome. So yeah, so today is the fourth and last lecture of this mini micro course, and today we'll be looking at something called the odd distance problem, and the official name is, I think, Rosenfeld's problem or something like that. But Rosenfeld was a very smart guy. He made a million different problems, so this is not a very unique way to refer to this. So we'll just call it the odd distance problem. So we have seen the Hadwig and Nelson problem. Okay, let me just change the pen. Hadwig and Nelson problem. And another name for that is um, Erdős's unit distance problem, which makes sense. Unit distance does feature in the problem statement. So based on this and some basic pattern matching skills, can anyone guess what the statement of the odd distance problem should be? This is not a serious math question or anything, just take your best shot.
Maybe we have to color the plane by a color such that distance between no 2 points of the same color is a odd integer.
That is precisely correct. So the problem asks,
We color the
yeah,
points if they are at odd distance apart.
what? Sorry,
We
say that
col
again.
we color to the points if they are odd distance apart, like because it's odd distance.
No, I'm not sure what that statement means. And anyway, the other thing was correct. So I'm just writing it down now. What's the minimum number of colors you need to paint the plane so that no two points with the same color have an odd integer distance between them. Yeah. So yeah. So for Hadwick-Nelson problem with this, call this number chi. So for polychromatic number of the plane, we call that chi p. The standard notation for this is chi odd R2, or sometimes just chi odd, when the fact that we are working on R2 is clear. So yeah, some of you may have seen. Okay, never mind. Yeah. So yeah. Yes, someone had a question.
Yeah, doesn't this sound very contrived? Like, why odd? Is there an integer distance problem without the odd condition?
Not that I know of.
So why is there an odd integer distance problem? Is it like easier because it just sounds very contrived?
It's not easy at all, but I think the integer distance problem is easier somehow. Haven't actually tried that. That's a good question. Uh, if I find something on that, I'll let you guys know.
Okay, thank you.
Yes. Yeah. So one of the main motivations is this. So in general, the idea is to understand the graph that the unit distance graph of the plane, right? So suppose imagine you're on R2 and you have an infinite graph in which every point is a vertex and two vertices are joined if and only if the distance is unity 1. Well, and then the Hadwick and Nelson problem basically asks what's the chromatic number of that uh, graph. Now, in general, the idea behind these kind of problems is to figure out some graph theoretic properties of the graph that this makes. Now, the odd distance graph, so to speak, there is some cool things. There were some cool things known about that at that point. For example, there is a classic problem. Uh, this was well known from quite some time. I don't know the dates, but so people had some notions of what the graph should look like. So people thought maybe we could make some more progress in this, and it turns out that's pretty hard. So I you may try this at some point on your own. I
Whose
won't.
pairwise distances or normal distances?
What do you mean normal distances?
Like if I consider 3 cross 3 square, then aren't this?
You have a 3 cross 3 square. That's a lot of points. We need only 4 points though.
Oh no, I mean the corner vertices of that.
Ah, okay. No, no. So you have to consider these distances as well, right? All odd integers.
Okay.
Yeah. So if you do that, these will be some root 2 times some nonsense, and that is not even an integer. So the idea is if you have 4 points and you want to make all of these 6 distances odd integers, that cannot happen. So the proof is actually a very cute application of matrix algebra, linear algebra. So I ask you to look that up on your own later, or maybe I'll send you a link or something. But so this is not a thing here. Point being, we had some idea what the graph, what sort of structure this graph has. In the sense, this basically says there is no k4 inside the odd distance graph of R2. But so you would think maybe there's some good coloring that can happen, and what turns out it's really hard. So let's do that. Hard problems are fun. So
Why is there no K4?
because okay, so this statement basically says there are no 4 points whose mutual distances are all odd integers, right?
Yes.
And if that's basically the same thing as saying there is no 4 vertex complete subgraph inside the odd distance graph. I
Yes.
haven't defined what the odd distance graph is, but maybe you can. This is not our main focus.
But we want such points whose distance is not odd. No.
What?
Distance
No, no,
or
no,
the
no. I mean, so the odd distance graph is basically you take all points in R2 and every point is a vertex and you join two vertices if if their mutual distance is odd integer, right? And this statement basically means that graph does not have a K4. Does that make sense?
But in R2 though we can have no. Like there are
How?
real numbers, so maybe someone.
I
Not
mean,
sure.
this problem says you can't. Do you have a counterexample in mind?
Oh, okay. There are odd integers.
Yeah.
Like
So, and the odd distance problem basically asks what's the chromatic number for this graph. So, anyway, long story short, we're gonna prove stuff about this. So, this current state of this problem is very wide open. But we do know some lower bounds. So, what's the obvious lower bound you can think of? I mean,
four at least.
how?
Like because of that K4 property.
Mm, Not really. It doesn't directly follow that. Okay, so we basically want to prove that there is no way to color this with four colors. The K4 property doesn't directly imply that there is no way to color that, right? Does it?
Yeah, no.
Yeah. So yeah,
I didn't
so
get this. Why isn't there any way to color this with four colors?
there I didn't say that. That's just one of the suggestions made by one of the students, and I'm saying anyway, ignore that. Point being, the current state of this problem is wide open, but we do have some lower bounds. So, for example, we could start by proving this is at least 3. So you can't color the plane with 2 colors as that. mm, well, no two equally colored points have odd integer distance.
Doesn't this follow from directly from the unit distance problem?
How?
Like if we color a plane by two colors, then some 2 points are a unit distance apart of the same color and one is odd.
If you color the, yes, that is correct. Uh,
In fact, chi of odd is greater than equal to 5 as we proved that chi is greater than
yes,
equal to 5.
yes. Hold up. So yeah, greater than equal to chi of what is that thing? Yeah, the actual chi. Yes, that is correct. So, but the proof for the lower bound of chi is fairly intensive and not fun at all. So let's try to derive some other lower bounds. Let's try to do this from scratch instead. So chi odd is greater than equal to 3 is easy to prove, as I said, because in fact it's greater than equal to 4 is also easy to prove, just because chi is equal to greater than equal to 4. And how did we prove chi is greater than equal to 4? Using the Moser spindle. So you can't color that. Now what we're going to prove is chi odd is greater than or equal to 5. This would follow, as you said, from the fact that chi is greater than or equal to 5. But let's be honest, no one really likes the proof of chi is greater than or equal to 5. So today we're going to find a more human, like more more human proof of why this is true. As always, the main idea is equilateral triangles. So what we're going to do is take a whole bunch of equilateral triangles. Essentially, draw this grid of equilateral triangles. Yes, and let's make these unit distance. So this is like a 7 side. Each side is has side length 7 in this entire equilateral triangle. Well, this number 7 is really not important. Um, so ideally, we would like to prove that this diagram cannot be colored with exactly 4 colors, but that turns out to be not true. In fact, if you're just looking at these points on this infinite equilateral triangle grid, they can in fact be proved by using they can in fact be painted by using 4 colors. So can someone, does someone want to try painting these points, just these vertices, with 4 colors, so that no two vertices have an odd distance apart are of the same color?
We have to paint this bigger whole rectangle.
You have to, sorry, say that again.
We have to paint this big rectangle, big triangle.
Yes, so what I'm looking for is a coloring of these vertices on the triangular grid, and we're just going to ignore every other point in the plane. So I claim this is 4 colorable. So what I'm looking for is the coloring of this triangular grid with 4 colors, so that no 2 points in any distance apart are
Okay, I'm
the
not
same color. Odd
sure,
distance.
but
Odd
like,
distance. You go on.
yeah, I'm not sure, but like we can do the leftmost point as suppose the color red, green, yellow, blue.
Mm-hmm.
So the red,
Mm-hmm.
and then in the bottom line,
Mm-hmm.
leave one point and then red,
Mm-hmm.
leave this red,
Mm-hmm.
and then leave this and red, and leave
Mm-hmm.
this and red. and similarly we
Nice.
do for all sides, and this is how we do red.
Okay, nice.
And also like in the how do I explain? Okay, so basically in this equilateral triangle there is one slanting side.
Mm-hmm.
So parallel to this, the third side, oh, fifth side, which has like one, two, three more points with the red points. We color the middlemost point as red.
Okay, I am very lost. Let's just give things names. Okay, so
Hmm.
let's say this is the x direction and this is the y direction. Can you give coordinates for your points?
Okay, in the third direction, it is.
Okay, cool. Uh, so hold on. So this is z direction. From where are we starting?
Yeah. So from the origin is the leftmost point. This.
Mm-hmm. This is the origin.
Yes.
Okay.
So one, two, three, one, two, three. On the fourth line, in the z direction.
And the fourth line, this one. Oh wait, sorry, this one. I'm bad at counting. Yes.
Okay, wait.
Oops.
Okay, in that case, it's the x direction. Sorry, fourth line in the
So
x direction.
this one. Okay, by x direction you mean the fourth line along the x direction, or
Wait, I will say parallel. Fourth line
okay,
parallel to z.
fourth line parallel to z. Ah, that makes more sense. So this one,
Yes, the middlemost point is red.
perfect. Yes, middlemost point is red. Ah, brilliant.
Yes. Then the sixth line parallel to z. Uh, the second point from top and the fourth point from top are red, like leaving distances too.
Ah, so like this.
Yes,
Ah,
these are
perfect.
red.
Yeah.
Okay,
Okay.
now in the bottommost line of the original triangle,
Mm-hmm.
between red and red, there is yellow.
Ah,
Suppose.
I get the idea now. So I can
Yes.
probably fill that in from now on. Yes. So these are yellow. So effectively, this does end up working, and this is the blue. What else? This is blue, and this is say some. What is the other color?
Green.
Green. Yeah. So effectively, we go along each line. This alternates R Y R Y R Y. This alternates R Y R Y. This alternates R Y R Y. And these alternates R B R B R B. And this alternates Y G Y G Y G, and so on. So that does give a correct coloring. And it's easy to check that along these grid lines, odd distance do have different colors. So that is okay. But here's the question: are all odd distances along grid lines? I mean, is it possible that this point and this point, for example, have an odd distance or something like that?
I think some of them, because of a rhombus, are a integer into root 3, so that's not a problem.
Okay, so that doesn't really prove that nothing here is. So this may not be a rhombus, right? So this is, for example, not a rhombus. This is the normal parallelogram. So there's no ratio of root 3 over here. So yeah, let me just give you the answer. So as it turns out, it's not true that the all the distances are along grid lines. For example, if you take this point, okay, this is way too messy right now. Let me just pick a different color. If you take this point, go 5 units along this direction, and whoops, my triangle is not big enough. And 3 units along this direction, you reach this. Turns out this distance is actually an odd integer. And we can calculate exactly how much. So in this triangle, this is 5, this is 3, and this angle, this is 120 degrees. So if you use the usual
7.
tricks, yes, correct. So this distance turns out to be 7. So, and this is not the only one, of course, there are plenty of more if you extend that to the infinite grid. But even considering those, this coloring does end up working. In this case, for example, this was R, and this would be G. So that does end up working out. So we have to prove that this does work. So what we need is some sort of, well, algebraic way to parameterize the points in this grid. So if this was a rectangular grid, for example, we could say the lattice points are of the form m comma n, where m and n are integers, but that's not the case here. The coordinates don't work that way here. So what would be a good way to parameterize a general point in this triangular grid?
I think we can basically define everything in terms of x and y axis only,
That is
which
correct.
have
And
60-degree angle, and then we can make a scheme that a number m, basically in this grid a number m comma n is colored red if and only if both of m comma n are even, both coordinates are even.
yes, that is correct. But what I want is basically, so it would be very convenient if we could just work with that. But in general, in this triangular grid, it's very hard to find the distance between 2 points m comma n and say x comma y, right? So what I want is the m comma n point expressed in terms of normal Euclidean coordinates. So let's do that. That's not actually too hard. So suppose we have m comma n. So that's,
I have one doubt here.
yes, go on.
Didn't you say that chi of odd is greater than equal to 5?
Did I say that? Yes, I did say that. Yes.
So you are saying that four colors do work.
Yes, I think four colors work just for this triangular grid. There are other points on the plane. We are not considering that at all.
I see.
So if you add more points to the plane, then things get a bit out of hand. So, but
Oh,
if you're
okay.
looking at just this subset of the plane, that is indeed four colorable.
Yeah, got it.
So let's get an expression for the mn point here.
And
So
can we prove that the curling we did is the only possible curling?
I think that is possible. Yes, you just start from the first equilateral triangle, and then the rest of the moves are all basically forced. So if you start from here, it should be possible to prove. I'm not going to do it right now, but it should be possible to prove. And I mean, up to recoloring and everything. So anyway, so what is I was gonna parameterize these points. So suppose the mn point. How would I parameterize that? I'm going m times in the x direction, and the y direction is really along the vector half comma half root 3. I'll let you check the calculations yourself. Basically draw perpendicular and do some usually Euclidean geometry stuff. So the m and comma point in Euclidean coordinates is really the point with these coordinates. And like I said, like someone said, this is colored 1 if m n even, 2 if m odd and even, 3 if n m even and odd, and 4 if m n both odd.
Isn't x-axis m root 3 by 2 in the Euclidean thing?
Isn't what? Say that again.
Shouldn't this be m root 3 by 2 instead of m plus n by 2?
What did I do? Yes, yes, right. Uh, so I meant to make this n. Yeah, yeah, correct.
No, it should be m root 3 by 2, I guess. This
Instead,
m plus n by 2.
okay, let me check my calculations again. Sorry. We are going m units in x direction, right? So that gives the m here, and n units in this direction. That gives the n here and here. Does that make sense, right? Hold on, what am I doing wrong?
Oh yeah, I think I messed up. Maybe you should interchange m and n.
Is there a good reason? Sure, why not? I mean, really matter.
No, I'm saying that this is wrong. Like not wrong. Maybe I'm misunderstanding because suppose we go 1 unit in if we take n equal to 1,
Mm-hmm.
then yeah, then now it is right because we go n by 2 root 3 in the y direction.
Mm-hmm.
So I like according to what are the exact coordinates? What is the exact transformation?
I'm not sure. Okay, so the mn point has coordinates this. That is correct, right? Is that the thing you're probably trying
No,
to?
I think this is not correct. Suppose you take n equal to 1. Oh,
Okay,
sorry, m equal 1. M equal 1.
m equal to 1. Sure.
Then it is clear that the y coordinate is root 3 by 2, right?
M equal to 1 means going 1 unit in this direction.
Above.
Ah, you are taking m as the y coordinate. So we basically have we are working with different conventions. Doesn't really, not that it matters, but sure, let's just stick to the normal stuff. Sure, I'll just switch m and n. So by m comma n, I meant the point you get by going m directions, m in this direction and n in this direction. But sure, this is probably more natural. Like, yeah, okay. So yeah, the coloring still is not wrong. I mean, you just switch around the colorings. So now
Isn't
you
it m root 3 by 2? I think root 3 must come in x axis also.
no, no. This is I'm fairly certain this is correct. Why should root three come in x-axis?
Oh, yeah, I messed up. Sorry.
All right. So yeah. So now to prove this is actually valid, so suppose we have 2 points, one n1 plus m1 by 2, m1 by 2 root 3, and other is n2 plus m2 by 2, m2 by 2 root 3, and they happen to be of the same color, let's say color 1. Now what is the distance between these two? If you calculate, that gives you n minus n2 plus m1 minus m2 by 2 whole squared plus m1 minus m2 by 2 times root 3 whole squared, and the square root of that, and if you simplify this entire mess, this actually simplifies to something pretty nice. Yeah. So we assumed these are both of color 1, which means m n1 n1 mo2 n2, they're all even, and if you use that in here, you will find that this is an even integer. If it's this thing inside is an even integer, so if at all the actual distance is an integer, it has to be even. So that proves that this coloring does indeed work and even takes care of weird non-grid line distances like this one. So this gives a forecoloring of the equilateral triangular grid, but the sad news is this means we cannot directly use this equilateral triangular grid to prove 5 colors are not enough. So, but we can glean some pretty important information from this. So here's the lemma. Suppose we have a forecoloring of the infinite triangular grid. Then 2 points inside. Let's give this grid a name, say T, and 2 points inside T with T, on T, in T, whatever. Distance equal to 8 have the same color. So that is pretty nifty. So let's see why that is true. I'm gonna draw large-ish equilateral triangle. At least I'm gonna try to draw a large-ish equilateral triangle. In no universe, this is looking equilateral, but whatever. Yes. Is that good? 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, cool. That should be good enough for our purposes. Now, if 2 points do have a distance of exactly equal to 8 units, then you can actually prove that they are on the same line. So it can't be anything like this and this. This is just pure number theory based on the calculation we did above the. I'll leave the details to you. So take 2 points, say A and B, exactly 8 units apart, and suppose they have two different colors. So suppose this is without
I
loss of.
think B should be the rightmost.
Is it 1, 2, 3, 4, 5, 6, 7? Yes, B should be rightmost indeed. 8. Yes, this is correct. Thank you, sorry, I'm bad at counting. Yeah, where was I? Yeah. So suppose A and B do have different colors for some reason. So suppose this is colored red and this is colored, well, actually this is going to be really confusing because the label also says B, so I can't call that blue. Let's write out the full names. Or just give numbers to the colors. So the colors are 1, 2, 3, and 4. So suppose this is colored 1 without loss of generality, and this is colored 2. Now we look at these 2 points. This line is 20. These 2 points, say C and D. What can we say about these 2 points?
C is not 1 and D is not 2.
Sorry, oops, yes. What about now? Yeah. C is not 1, that is correct, because C is a distance 3 from A. What
Yeah,
else?
both of C and D are not 1 and not 2, so they are 3 or 4.
Yes, C can't be 2 because C is the distance of 5 from B. So this is without loss of generality, say 3, and this is 4. Cool, that is pretty cool. And what about this point? Let's call this.
No, they can be same also, 3, 3.
All right, they can be same also. So let's forget about B for now. So yeah, where was I? Yeah. So this is a different color called as 3. And what about this point? Let's call this one D instead. Yeah. What can you say about this point D?
This
Yeah.
is not 1, and
This is not 1. That is correct.
not
And not
2,
3.
not
Not
2,
3.
and not
That's
2
also
because it is at
because
7.
yes, correct. So this is where we use the fact that this distance is 7. So this can't be 1, 3, or 2. So this has to be the fourth color. Let's say this is the fourth color. Oh, and there are way too many numbers on the screen. I'm just gonna confuse myself with this. Cool. So yeah. Uh, where was I?
Yeah, you proved DS4.
Yes, yes, correct.
Okay, now I
So,
think we can do one thing.
mhm,
Symmetrically, just
mhm.
consider the third point on the rightmost edge, 3 points above.
Yes, this one.
Yes, this
So
should be
let's call
also
this.
4. This should
This
also be 4 by similar
mm,
logic. But now,
not hold up, hold up. Not necessarily. See, for this logic, we use this point, right?
Oh,
So
okay,
for this
okay.
logic, we would use this point, but this could be 4. So in that case, this would be 3.
Oh no, you have to consider the point 2 units up from me, and that must be 4.
Actually, since one of you mentioned this point, there is something we can say about this point E.
Oh, this should be, I guess. Oh, okay.
Yeah, actually, this there is something you can say about point E. What is it?
Yeah, this is 3.
This is 3, correct? Because it can't be 2 because this is 3 unit distance from here. This can't be 1 because this is 7 distance away from here. This can be 4 because
D and E are
D.
5 units.
Yes, correct. So this has to be 3. So yeah, that is pretty good. And what does that say about this point here?
Must be 4.
Yeah.
Absolutely. This can't be 2 because of this. One can't be 1 because of this. Can't be 3 because of E. Perfect. So we are in pretty good shape. And so we basically just keep going with this logic and see where that gets us. The next point to consider is G and H. What do you think the colors of G and H should be?
H must be. Uh,
It is not
H
1.
must be 4. H must be
Yes,
4.
H must be 4.
And G must be 3.
Yeah.
G must be 3 and H must be
4.
4. I'm not going to go through the details again. It's basically more or less the same logic over and over again. So, yeah. So, yeah, that is pretty good. And now for the finale, we consider these 3 points. Let's call them X, Y, and Z. You probably can't fix the color of any of these, but there's at least something you should be able to say. Yeah,
Oh, do we basically show that two of them are of the same color?
effectively, yes. Okay, so what are the possible options for the color of X?
It is not 3.
It is not 3 because it's, why is it not 3 again? Ah, yeah,
Oh,
this is because
because of
it's
A.
E, yes, correct. And it's not,
4 because
it's
of
not
F.
4 because of F.
Basically,
Uh,
I think we can prove that each of the points X, Y, Z is not 3, not 4.
Correct. So X has to
Yeah.
be either of 1 or 2. In fact, by same logic, because of D and C, Y also has to be either 1 of 2. And same with Z. It has to be either 1 or 2. So, but there
Yeah.
are 3 colors and so 3 points and 2 colors, and pigeonhole principle gets the rest done for us. So yeah. So we have proved this lemma. So um, 2 points in T that have distance 8 always have the same color in this triangular grid. So recall way back in lecture when we introduced a heuristic. What do we do when we know for sure 2 points must have the same color?
Like we just consider a 8, 8, 1 triangle.
Yes.
Absolutely. So we
Now we
basically
consider a 8 odd triangle.
8 word triangle or 8 word triangle, anything works really.
I mean odd. 8
Yeah,
odd.
odd. I mean, one is odd anyway, so it doesn't really
Yeah.
matter. So yeah.
Okay.
So since we are looking at entirety of R2 now, we are allowed to go outside this grid. We have already shown that staying inside this grid does nothing good. So in staying inside this grid is useless. So since we want to prove 4 colors does not suffice, we can go outside the grid and we basically can take a copy of this grid, and by same logic, this is color 1. By same logic, this should be color 1 as well. And we can rotate this sufficiently so this distance is any odd integer we want. And that's a contradiction. Yes. So that proves odd is at least 5. Yay. So any questions so far? Is this clear?
Yes, clear.
Yeah, perfect. Now you would expect some nice coloring for upper bound. Fortunately, that is not known. There is currently no known upper bound. There is a known construction with exactly countably many colors, so that no 2 points with odd distance have the same color, but that's very useful because that's like infinitely many colors. And in fact, it's expected that infinitely many colors are necessary. But no one really knows the proof. So recall when in chromatic graph problem we had reduced the number to this tiny set 5, 6, 7. Now we have this humongous set 5, 6, 7, 8 that goes all the way up to infinity and no one has no clue. So there's nothing I can do about that. And in fact, when I say expected, we very strongly suspect that their infinity colors are actually necessary in the sense that there it has been proved that your so how do I say this? So remember all the colorings that we did for proving upper bounds were very nice colorings in the sense that some polygon we took and we colored that entire area blue, and some polygon we took and we colored that entire area green, and so on. So each of the color classes were very nice set. They are not pathological random nonsense. And in math, there is a notion of something called a measurable set, which means sets that you can assign a notion of area to. And it has been proved that if you're only using color classes that are measurable sets, then infinitely many colors are indeed necessary. So either there's a very nonsense, insane coloring that gives you a finite bound, or infinitely many colors are actually necessary, and no one really knows.
So, sir, can't even computers, very strong computer, find the answer of these questions?
Not really. There are kind of way too many points on R2. Yeah. So, and if the answer is indeed infinite, then computers can't really do a lot of things. But let's see, there's some.
And have mathematicians prove any other bound than greater than equal to 5, because they suspect infinity, so they might have proven.
Nope, 5 is the best known. I know, it's disappointing. So, well, but at least this is a nice proof. Yes. So, what else? Another thing people have looked at is, yeah, go on. There is someone who has a question.
Yeah, and about countable, is proving countable easy or very tough?
Proving that countable colors are sufficient is not very hard. In fact, maybe I'll just leave that as an exercise. Actually, maybe this is. Yeah, countable is not hard at all. Actually, let's just see the. I'll give you 2 minutes to think about it. Here's a hint. Tiling. Tiling is always the answer for upper bounds. That is tractable upper bounds. No nonsense constructions.
Can you repeat the question actually?
So yeah, the question is try to color the plane with countably many colors, such that no 2 points with an odd integer distance have the same color.
I think we have to prove that we can color with uncountably.
I mean, uncountably many colors is easy. Just give every point a different color.
Oh,
It is possible to color it with countably many colors.
Do we do the same thing? Consider the center of the hexagon.
What do you mean?
Like considering the center of the hexagon and drawing equilateral triangles, 6 equilateral triangles.
Sure, and what the coloring is like. In fact, you don't even have to go to hexagons. Let's just go through an easy proof. Just partition the entire plane into squares and take very small squares. Let's say each side is like 1/10 unit or something. And since there are countably many squares, you can give each square a different color, and that's pretty much it.
Oh.
why is the number of squares countable?
So this is like set theory. n cross n is bijective with, sorry,
Yeah, n
uh,
cross n I know.
and since n is isomorphic, not isomorphic, equinumerous with z, z cross z is also bijective with z.
Oh, so we basically project from n to n to n
Sure.
cross n to z cross
Yes.
z.
Effectively, I mean, you can just maybe if you have a countable list of colors, you can sort of start here and sort of spiral around, well, in this pattern, and it should be visually obvious that that eventually gets all the squares anyway, right? Yeah. So that proves countable colors are enough, but that doesn't prove anything significant. So yeah, if since I was gonna talk about the chromatic number of Q2, this is terrible notation. So what happens if we restrict ourselves to only points with rational coordinates? In our above example, we had this entire equilateral grid, and many of those points did not have rational coordinates. There's plenty of root 3s. So what happens if we restrict ourselves to only rational coordinates? The answer turns out to be fairly simple in this case. In fact, yes, in fact, you can prove the graph in this case. This graph,
Oh,
this is bipartite.
q square is the Cartesian plane with rational coordinates.
Yes, Q square is the set of all points with rational coordinates, both coordinates rational. Okay, so
Yeah.
this turns out to be bipartite. And what can you say about the chromatic number of a bipartite graph? Does
Just
everyone know
two.
what a, yes, that's two. Does everyone know what a bipartite graph
So
is?
Yeah.
yeah.
Okay, if anyone does not understand the words I'm saying, just interrupt me and let me know.
But like bipartite in what sense?
In the sense that you can, okay, so graph is bipartite if the set of vertices can be partitioned into two sets x and y non-empty, says that no vertice, there are no edges between inside x and there are no edges inside y.
Yeah.
And another definition is there are no odd cycles, and you try to prove yourself that these two definitions equivalent.
What is the odd cycle one definition? I don't know that.
So yeah, so here's the lemma. G is bipartite if and only if G has no odd cycles. Odd cycles, by odd cycles, you know what a cycle is. This is a cycle, and the cycle is odd if it has odd vertices or odd number of edges.
Yeah.
So the converse should be, I mean, I'll just let you. So proving this is not very hard. I'll just outline a series of steps and you can try to fill in the details. So this is the main lemma we'll be using, and there's some other things on the way. So this proof is essentially just number theory. So step one, if x, y, z are integers so that then z equals 0 mod 2 implies x and y are also 0 mod 2. And if there is 1 mod 2, then x is even, y is odd, or vice versa. This is just modular arithmetic. I trust you can show this for yourself. Step 2 is showing XYZ be a integers. Is that then if 2 power k divides z square, 2 power k divides z, 2 power k also divides x, and 2, 2 power k also divides y. Any idea of how to prove this? This is not too hard. Not a complete proof. I was just looking for a one-line answer. Yeah, the one-line answer is just induction. So you use this lemma, since z is divisible by 2 power k, it's also divisible by 2. So x and y will also have to be even integers. Then you can sort of divide out the entire equation by 2 and use induction hypothesis. So leave it to you guys to fill in the details. This is a slightly harder statement. So till now we are only working in integers, and we need to make a jump to rationals at some point, and this is where that happens. Suppose x is the point xy, which is also 2k power n to ln. U is the point uv, which is 2p power r 2qs. So x and y, u are both rational points, and every rational number can be written as 2 power some integer, maybe negative, times some odd number. This is something, convince yourself of this. And we have written these things in that way.
Like 1 by 6 cannot be written in this form.
1 by 6 can be written as 2 power minus, hold up. If you do multiply, hold up. Yeah, that is correct. I don't know why I just said that. Hold up. Anyway, sorry, never mind that. So consider numbers that can be written in this form for now. And then, so this here, k, l, p, q, they are integers, and m, n, r, s, they are odd integers. So in this case, if the distance between x and y is odd integer, then x minus u, y minus v are both integers with different parities. Proving this takes a little bit of work, but I don't have time to go through all that work, so I'll just, as always, leave this checking to you. Yes, now comes the fun part. If you assume all of this, then we can easily prove that this odd distance graph for Q2 is bipartite. How? So suppose not. Suppose it does contain an odd cycle. Suppose xy y1 xn yn is an odd cycle in Q2. So what does that mean? N is odd, and the distance between x1 y1 and x2 y2 is an odd integer. The distance between x2 y2 and x3 y3 is an odd integer, and so on, all the way up to xn yn. And the distance between xn yn and x1 y2 is also an odd integer. So suppose this does happen. Now, you can always sort of, yes, you can sort of always multiply these by, you can sort of always write these as ki ni by m and li not pi by n. So what we're doing here is we are basically looking at all of these rational points, and we are sort of taking the largest possible common odd denominator. First, we sort of absorb out the power of 2 in each of these, and all everything that remains is some odd number divided by some odd number, and we make the denominators in the odd number all the same by multiplying by a sufficiently large odd number. Is it clear that we can always do that?
Basically, we are making it to the previous form, right?
We're basically making it to the previous form, except we included the denominators and below, and yeah, we're basically making it to the previous form, and we're making sure the denominators are all the same.
I think the denominators all cannot be same. Basically, we can remove the denominators by scaling by odd number, and odd into odd is odd.
Yes, so
So I didn't get this odd logic,
okay, just
denominator logic.
so what we are doing here is, suppose the points are something like 3 by 5, um, 3 by 14, and I don't know, 4 by 5. So what we will do is, first we will absorb out all the powers of 2 that is in there. So this is written as 2 times 1 by 7. This is written as 1 times 3 by 5. This will be written as 2 power
Can
minus
we
1 by.
replace that 5 on the right by 13?
Sure. Okay. And this can be written as 1 by 1 by 13. Right? Now what we do is we multiply all of these denominators by, we make all the common denominators 7 times 5 times 13. I don't want to calculate what that is, but in any case, this would be something like 5 by 13 times this. This would be something like 3 times 7 by 13 by
Yeah, got
this.
it.
The rest you can figure out on your own. Yeah. So
Basically, we can remove even the denominators because odd into odd is odd.
perfect, correct, exactly. So we have expressed all the coordinates in this form: 2 power something times some odd number divided by some odd number. And what's more is, you can actually assume m is equal to 1, because if not, you can sort of scale the entire diagram by m, and the distance between 2 points is still odd because you're scaling up by an odd number, right?
Yeah.
Yes. All right. So what this means is these points all the way up to 2 per kn n1, 2 per ln. Okay, shouldn't have chosen n for this. Let's say this is 3. Oops. Yeah, 80 nt and 20 nt. This is also an odd cycle, and we know how to deal with points of this form already. Because of our lemma, this means 2ki ni minus 2ki plus 1 ni plus 1 and 2li ni, sorry, not li, pi minus 2l and pi plus 1. These are integers with different parities. Yes, this is just the lemma that we stated before. X was this thing and u was this thing. So you plug these things in and you get that these integers are all of different parities. But the thing is, when you add these things all up, not writing this again, you get a big zero because stuff cancels out. And the sum of these two things is odd because they have different parities. And so we have a situation where an odd number of odd things added gives zero, which cannot happen. So this is a contradiction. And therefore, this graph was bipartite. So yeah, this is where I'll stop now. Any questions? I mean, there should be plenty of questions. I did not fill in any of the details, but any questions that I can fill in right now.
I think it was fine.
Okay. Okay. Cool. I'll send you guys links to some of these resources in the Discord chat later on.
Any
So
particular motivation behind the last lemma you mentioned?
that is effectively just so since you're looking at odd numbers, it's natural to look at what happens when you take out the even sort of uh, how do I say this? The even part of each coordinate, and then you get that you have to look at numbers of this form, right? And then that means it's useful to look at what happens when two number points of this form have an odd distance, and you sort of crunch the numbers and come up with a guess of this sort. Yeah. All right, sure, I'll do that. Cool. Any more questions? All right.